This is a joint work with Bombach and Ibragimov. Okay, so this is a topic on graphs, not on strings. Okay, so for maybe okay, so the problem we consider is the comparison of two graphs, or you can also call networks. And what are we doing here is that we given two graphs, and we want to say how similar is the second graph to the first one. Okay, we can, in biological applications, it's often called network alignment. We want to find a correspondence between the nodes of the two graphs or networks. Okay, so here is an example. We have 5 nodes here and also 5 nodes in the second graph. And we can say the red one can be mapped to the red one here, and so on. But we say that there are 2 edges here, one in the first graph and one in the second graph. We cannot find the corresponding edges for them. Okay, there are some mistakes. Oh, they are similar, but not identical, these 2 graphs. So what is the motivation? Yeah, this is actually a comparison of graphs. This is one of the most well-studied problems in graph theory. For example, it can find application in bioinformatics. Okay, given protein-protein interaction networks, which is somehow look like this. The loads, they represent proteins, and edges. We add an edge between 2 proteins if they have some kind of interaction. So these are the number of nodes and edges in a typical protein-protein networks. And it's also known that this kind of PPI networks, they are not that the edges, the existence of edges, are not that confident. Okay, there might be mistakes in this network. Oops. So what do we want to do here? We want to find the proteins between these 2 PPI networks, which are evolutionarily conserved or functionally similar to each other. And then, for example, if we have some here, a correspondence between these 2, a dog and I don't know what's that, so bacterium. So we assume that the things which are closed to the dog and their images in the other networks should also be closed to the image of dog. Okay, so this is the biological motivation application of this network alignment problem. So in the graph theory, okay, so the best case of network alignment is that we have a perfect match between 2 graphs. These graphs, they are identical, only the layout may be different. However, that is not a case we always have in the practice. So actually, normally we have 2 graphs. They are similar, but not identical. So the perfect case is not the normal case. In the graph theory, then we have this approximate perfect matching. Okay, this is called a problem graph edit distance. So there we have as input 2 graphs, and we want to add some vertex to the first graph, delete some vertex from the first graph, add some edges, and delete some edges, such that at the end, we get the second graph. So this is an example here. We delete this guy and add a new vertex here, and delete this edge, add a new edge here. Then we have the second graph. So, but it is known that graph edit distance problem, this is a very hard problem. Okay, for general graphs, there's almost nothing, no effective algorithm to compute the exact solution, optimal solution for this problem. Even not a good approximation. And even for the special graph classes, like trees, forests, and it's known that it's NP complete if we are given a tree and a forest. And the forest is even a collection of stars. And now we are asked to add edges to connect the stars to the given tree. Even that problem is hard. It's NP hard. So this is a quite simple problem, right? We have only stars and a simple tree. But even that case, we don't have efficient algorithm. Okay, so, but we have to solve the PPI network alignment problem. So then we try to look for other formulation of the comparison of graph problem. So this is one model we want to define for comparison of two graphs. So again, we have two graphs, okay? The first one, G1, and the second one is called G2. And we defined a concept called closed list. So what do we mean here? Do we mean here that is for a vertex V, okay, this is a vertex V. If it is mapped a vertex here in G2, then the labels of V, labels which we don't mean that the normal labels, we mean that the vertices which have small distance to V. Small distance is, that means the distance is bounded by a parameter L. Okay, this is the labels we mean here. So, and we say that these labels are mapped to some vertices here closed to the image of V, means that the total distance of the images of the labels to the image of V, the total distance, the difference between this and the total distance here is bounded by a parameter D. Okay, LV is the total distance of the labels of V to V, and LV prime is then the total distance of the image of the labels to the image of V. Okay, I hope that should be clear that here we say that if we say this L is 1, these are the direct labels of V, and here we say that the image of these labels, they are not directed labels of the image of V if we allow D equal to 2, okay? So two labels here could be mapped to vertices which have distance 2 to the image of V. The total distance here is 5, and here is 7. And the difference is bounded by the parameter D. Okay, so let's say some example, more example here. So if we consider the labels which have distance at most 2, and the difference is bounded by 2, okay? So we can see that here, this is V, okay? The vertices have distance 2 to this V are these guys. And now, if we map this vertex to this guy in the second graph, and we can see that the black ones, okay, have the same distance to the image as in the first graph. And here, these two have also the same distance to this guy. But you can see here, these two guys, they are now mapped to some vertices which are a bit far away from the image of V. Why can we do this? It's because that we reduced the distance of these two guys, reduced them, we mapped them to some direct labels of the image of V. We reduced the distance for these two guys such that we can increase the distance for these two vertices. You can get a bit feeling now. We have a very flexible mapping, actually. So consider now the graph isomorphism problem. So where we really require that the neighborhood should be identical in both graphs. And the labels of labels, labels of labels of labels, so on, so on, so on. And here is quite relaxed, actually. It's a generalization of this graph isomorphism problem. Okay, we consider not only the neighborhood, we consider the distance between the vertices. So we can now say that this distance between two vertices, which are directed labels to each other in the first one, this distance can be arbitrarily large between their images. Okay, if we think that for these guys which have distance 3 in the first graph, now we can map them to some directed labels of the image. And then we can then increase the distance between the image of these two vertices arbitrarily. So therefore, you can say that this is not a local constraint mapping between these two graphs. So another model we introduced last year is that we don't consider the total distance of these guys and the images. And we required for each of these labels. Okay, this has distance d, and the distance between their images must be bounded by d for each of these guys, for each of these labels. This was at Watson last year. And you say that this is a bit not as flexible as the new model. And because we require that for each of these labels, we require this distance upper bound. Okay, this is the model, the definition. And in this paper, this is a result actually of the results of this paper can be summarized in this table. We see that, unfortunately, we see that for only for very small values of these two parameters, we can get some polynomial result. Otherwise, it becomes NP hard. So this is, we consider it, we studied only on trees, okay? The reason is clear. First, it's easy to think that it's hard on graphs. Second is that our main motivation is from the PPI networks. And it's known that PPI networks is a very sparse graph. A very sparse graph. It has a large subgraph which is somehow like a tree. Okay? So therefore, if we can have some positive results for trees, we can use it for PPI networks. So we can try to generalize. So the most simple case is that L is equal to 1, D is equal to 0. So this is actually the same problem as a tree isomorphism problem. So a bit tricky is that for the L equal to 2, we consider vertices which have distance 2. And D is 0. Here, actually, we can prove that it's almost the same as tree isomorphism problem. The distinction is that for tree isomorphism problem, we map these leaves to this guy, and then this node must be mapped to here. But with d equal to 2, L equal to 2 here, we can switch these two. We can map this guy to this, and this to this. And you can see that it's still OK. So these are the simple case, and we have several NP completeness reductions for different cases. And all these reductions are from 3 partition problem. I will also only show the first one. So 3 partition is a problem defined as with input being a set of integers a1 to a3n. And the question is that, can we find n subsets of the set of integers a such that the integers in each subset has a sum equal to b? Okay, so therefore, the total sum of all these integers is nb. Okay, we have them partition them in this subset a1 to an such that each subset admits a sum b. This is a very classic NP complete problem. So can see this is an example here. This is a basic gadget for the reduction. For here, we have a D tree and a R tree, the name. So D tree has a root. Let's say it as a rooted tree. 5 minutes? OK, thank you. So this is a root, and this we have B identical subtrees under this root. And each subtree here is again a star with A leaves. And then the R tree is that we put only 2 leaves from these 2 subtrees to the root. And it can be shown that this can be mapped to this. D tree can be mapped to R tree with these parameters. So then we can construct now the reduction. So with this part, encoding the integers 3n, and this is a big D tree, and this is a big R tree, which together guarantee that this guy must be mapped to this guy. Okay, and this large D tree must be mapped to this R tree. And then we have then n such blue parts, and each of them here has so many vertices, so many passes. Okay, length 2 passes. Okay, this is 1 and 1 and 1. Okay, we can say that actually if we have a partition, then we have to move this part here to here. And 3 integers to 1, 3 integers to 1. And the size of them must equal to now totally b. Okay, this is the idea of the reduction. So for this is the most complicated case. This is a polynomial time case. So this is an algorithm with 2 phases. One is top-down and one is bottom-up. Okay, so I don't have time to go into it. So finally, for the conclusion, so first we consider now the version to minimize the total error over one node. Okay, so maybe we don't know whether if we minimize the total error over all nodes, whether that can be polynomial time solvable. That allow us more flexibility if you can consider it. Okay, maybe this is also how to derive the approximation algorithm for these versions. And we started to implement some heuristic for this problem, and it will be available at Gecko this year. Okay, that's all. Thank you.
Questions?
Okay.
Do you think that the approximation algorithms for the CPM-based models can be upper bounded by the unique games conjecture-based proofs?
Oh, we didn't think about it. I don't know.
Okay.
Why do you have that feeling?
Because the one interpretation of the unique games conjecture is the constraint satisfaction of the constraints on edges, so it's remembered me that, so maybe there can be some type of connection about it.
Mm-hmm. Thank you for that.